What are adaptive PWM algorithms and how do they work? Imagine controlling a motor or a power converter so smoothly that it adjusts itself automatically to changing conditions. That's what adaptive pulse width modulation algorithms do. They are control methods used in power electronics to change how they operate in real time, based on what the system needs at that moment. Instead of sticking to a fixed pattern, these algorithms tweak the switching frequency and duty cycle as the system runs. This makes power systems more efficient and reliable, especially when dealing with renewable energy sources or variable loads. Let's start with the basics. Pulse width modulation is a way to control how much power is delivered to a load. It does this by turning the power switch on and off rapidly within a fixed period. The ratio of the time the switch is on to the total period is called the duty cycle. A higher duty cycle means more power delivered. This method is popular because it controls power precisely without wasting energy as heat, unlike linear regulation. Now, adaptive pulse width modulation takes this a step further. It uses sensors and feedback loops to constantly monitor system parameters like current, voltage, or load conditions. Based on this data, the algorithm adjusts the switching frequency and duty cycle on the fly. For example, if a motor is speeding up or slowing down, the adaptive algorithm changes the switching pattern to keep the motor running smoothly. Similarly, in power converters connected to the grid, it can modify the switching to reduce harmonic distortion and improve power quality. One common approach in adaptive algorithms is to include a control layer that manages the switching frequency. This layer can change how fast the switches turn on and off depending on the system's needs. For instance, if the load is light, the algorithm might lower the switching frequency to reduce switching losses. If the load is heavy or the system demands quick responses, it can increase the frequency for better control. Some algorithms use model-based control, where they estimate system parameters in real time and adjust accordingly to handle uncertainties or changing conditions. In power electronics like inverters or active power filters, adaptive pulse width modulation can help improve the waveform quality. It can reduce harmonic distortion by adjusting the switching patterns based on the sensed line, currents, and voltage waveforms. Techniques like space vector modulation are often used, which representing the output voltage as a vector in a complex plane. Adaptive algorithms can modify these vectors dynamically to produce cleaner, more sinusoidal waveforms. The benefits of using adaptive pulse width modulation algorithms are clear. They boost efficiency by reducing switching and conduction losses. They improve power quality by minimizing harmonics and correcting power factor. They also make systems more robust, as they can adapt to changes in load or environmental conditions without manual intervention. Plus, they enhance the dynamic response of motor drives and converters, making them more responsive and stable. In summary, adaptive pulse width modulation algorithms work by constantly observing system variables and adjusting the switching frequency and duty cycle in real time. This ongoing adaptation results in more efficient, stable, and high-quality power conversion. They are especially useful in renewable energy systems and power electronics where conditions can change rapidly and unpredictably. These algorithms help make modern power systems smarter, more reliable, and better suited to handle the demands of today's energy landscape.